Hey everybody! In this video, I will be talking about how scientists separate mixtures. This will be very surface level, but it will be more than enough for an introduction. First, we will talk about how we separate heterogeneous mixtures. Our first obvious way of separating matter is using our hands. For example, in the image, the person separated a bag of M&Ms into the individual colors. We can use our hands to separate large objects like M&Ms. We can also use droppers to separate, for example, two different liquid layers. But scientists like to use something more professional. They like to use something called a separatory funnel, written over here. So how do they use a separatory funnel? Well, basically, you put the liquid in here, and we have two distinct layers that form, and then you use this valve to just drain off the blue liquid, leaving the yellow liquid. So that's a more professional and, honestly, a better way to separate two liquids. And two liquids that are in separate layers is a heterogeneous mixture because we can easily separate them. So remember to remind yourself about the definition of heterogeneous mixtures. And we can also separate heterogeneous mixtures by using a magnet. So for example, these paper clips are maybe attracted to these magnets, so they cling onto them, while maybe in the pile you have other stuff that's maybe not attracted to the magnet. So by using the magnet, you're separating the magnetic stuff from the non-magnetic stuff. So of course there are many ways to separate heterogeneous mixtures, and we just went over 4 of them. So I hope you have a better idea of how heterogeneous mixtures are separated. Now what about homogeneous mixtures? Remember, homogeneous mixtures are mixtures where the components are hard to tell apart. So you can't just use a dropper to separate, two liquids that are well mixed together and form a homogeneous mixture. There are other methods to separate homogeneous mixtures. In our first example, we will be looking at distillation, where we basically boil a solution to separate things, aka adding heat. For example, in this image, we're adding heat by using a Bunsen burner. There are 2 main types of distillation. In simple distillation, we straight up boil the solution until all the solvent disappears, leaving the solute behind. So let me draw a saltwater solution right here, and let me indicate these blue circles as water, and these red circles shown over here as salt. So let me draw another flask showing what happens when you boil off the solvent, aka the water, leaving the salt behind. So we're going to have the solute, or the salt, left over in the flask, while the solvent, the water, will have turned into a gas because boiling turns water from a liquid to a gas. And the water molecules are still intact, but they're moving faster because you added heat to them, which turns them from a liquid to gas, and that's why they escape the solution. So you're left with the solute. So let me continue my discussion about distillation. So when we distill water made of table salt, water has a boiling point of 100 degrees Celsius, so 100 degrees Celsius, while salt has a boiling point of, 1,465 degrees Celsius. So when we boil off the water, we are left with the salt. Well, why is that? Because when you add heat, you're adding heat until it reaches around 100 degrees Celsius, then the water will start boiling off at this temperature, but the salt will not boil off because salt has a boiling point of 1,465 degrees Celsius, so therefore it'll stay as a solid. And that's how distillation works, is that when you add heat to the solution, all the water will escape, leaving the salt behind. remember, this is a mixture, meaning that they're combined physically. So if you combine salt and water physically, there's a chance that you'll be able to separate them physically by heating it. So let's get back to the first diagram. When we vaporize the solvent, we usually want to collect it. And to collect it, we collect it through this device over here, which is the receiving flask. So what happens is that these little blue molecules are probably water molecules that are in its gaseous form, and what they're doing is that they're going here, and then they're going to flow down this tube, and then they're going to drop down here. And while they're here, they're going to go from a gas to a liquid. Now, why is that? Well, this tube over here, this tube where I showed the path of the water vapor traveling, actually has something surrounding it. There's this kind of layer made of glass surrounding it that has water flowing around it. And, let me undo all this because it's getting kind of messy. I'm going to erase that. So this tube over here, this part shown in blue, not the white part, the blue part, the layer that's surrounding this tube that's allowing the water vapor to go in is called a condenser. Now, this condenser will have water constantly circulating in it, and this water that circulates throughout the layered tube thing will absorb the heat from the gas, thus turning it from a gas to a liquid. And note that the water will only be touching the outside of the tube, so it won't be going into the white part here and going in here. No, it stays outside, and the water just kind of flows back in and out. And remember, this is cold water, so that we can actually cool down the gas and turn it into a liquid and condense it. So that's what a condenser is. Now let's talk about fractional distillation. Fractional distillation is basically the same thing as simple distillation, but this time you're going to be separating liquids with very similar boiling points instead of simple distillation, where you're separating things with huge boiling point differences. Like for simple distillation, we separated water and salt. Water has 100 degrees Celsius boiling point, and this salt, NaCl, sodium chloride, has a boiling point of 1,465 degrees Celsius. So it's a huge difference. But on the other hand, we use fractional distillation when we're measuring boiling point differences that are not as large. For example, maybe between 400 and 370, which is a difference of 30 degrees Celsius. So different liquids in the mixture, so for example, this might be our mixture, will vaporize and settle on different, columns of the fractionating column. So this is actually best shown on this image over here. So this fractionating column will have different layers that are at different temperatures. So this layer will, have a temperature of 400 degrees Celsius, while this layer will have a temperature of 300 C. So let's just say that the liquid, which is maybe down here, is composed of many different liquids that are mixed to the point that they are homogeneous mixtures. So we want to separate them. So let's just say one part of the mixture, maybe it's like the special liquid, this very special liquid, has a boiling point of, let's just say, maybe 320 degrees Celsius. Like, why not, right? So this liquid, of course, will start at the bottom very hot. So since this part right here is 400 degrees Celsius, and that's greater than our boiling point of 320 degrees Celsius, it will stay as a gas. Now, let's look at the next layer. So let's just say this gas continues traveling up these little, these little holes. It gets up to 370 degrees Celsius, but 370 C is still greater than 320 C, which is our boiling point. So this will still remain as a gas, and it'll keep on flowing up to 300 degrees Celsius. And then it's like, oh, wait a second. The temperature in this part is less than the boiling point. So now all our gas will start reverting back to a liquid. So we're going to have a liquid here, and it might drain down here. And in this case, diesel oil apparently has a boiling point of, between 370 and 300, because it obviously condensed here, and it's, flowing here and being collected by petroleum companies, because, this is oil stuff, and, it's being separated into gasoline and stuff, so this is obviously related to oil. So now let's look at another topic. Let's talk about chromatography. There are many types of chromatography. In paper chromatography, we separate things based on the polarity of the different components of the mixture. Now, what do we mean by polarity? Well, some chemicals are more electrically charged than other chemicals, and we abuse that fact in order to separate the chemicals. More detail about polarity will be discussed later on, but what we have in this image is basically a piece of chromatography paper, which is shown right there. And we have maybe a drop of the liquid mixture at the bottom, so in this case, the liquid mixture might be maybe the dot labeled 3. And what happens is that we dip this paper along with that dot, which is the liquid mixture that the paper absorbed, into a liquid solvent like water, which is, that stuff over there. And what will happen is that this liquid mixture in that dot labeled 3 will slowly travel up the paper along with the water, of course, and it will separate into different colors because, as I said, some chemicals have more charges than other chemicals, which is this idea of polarity, which we won't get into, but basically they're separated using water and based on polarity, aka charges. So now let's look at gas-liquid chromatography, which is right here. Whoa, it moved, huh? In gas-liquid chromatography, we boil a liquid mixture. So, for example, here is the sample injector, which is where our liquid mixture will be, and we boil it until all of it becomes a gas. So technically in here, all of the liquid has converted to gas, and it's our little mixture that we want to analyze. So we shoot something inert, so meaning non-reactive. So inert gases include helium, nitrogen gas, and hydrogen gas. So we might shoot these inert gases into this sample injector, and then this gas will basically push the sample gas that we have through these hoops. And let me just undo those hoops. So these hoops have a liquid coating on it. So let me just draw like a liquid coating. So things that like to be liquids will stick onto this liquid coating. Now, what do we mean by things that like to stay liquid? Well, things with high boiling points like to stay liquid, because if you have a high boiling point, it takes more temperature, or like a higher temperature, to turn you into gas, which means you're more resilient to turning into gas, or in other words, you like to be a liquid. So things with high boiling points will like to stay as a liquid. So what will happen is that the things with high boiling points, and what I mean by things is the substances inside the mixture, the substances that have high boiling points will get stuck to the tube and, the liquid that's coated on the tube, while things with low boiling points and, want to stay gaseous will flow right through the tube with ease. So the first things that we are going to detect are the things with low boiling points, followed by things with higher boiling points. So as you can see, this device separates the substances by boiling points, and it uses a detector to tell us, which parts of the substance we see first. And, it will tell us, what exactly there is inside the sample that we have. And this is commonly used in crimes when they have to find out, what's in that mysterious liquid. So they have to do this gas-liquid chromatography. Now, why is it called chromatography? Well, chromatography is defined as the separation of a mixture, like a homogeneous mixture, by passing it through a medium so they can move at different rates. In paper chromatography, the components of the mixture diffuse up chromatography paper via water, which is the medium. In gas-liquid chromatography, the inert gas, which is shown right over there, is the thing that helps push the rest of the gas found in the sample injector through these hoops and into the mass spectrometer detector. So let's talk about one more thing. This time, we're going to talk about something that is not really related to mixtures, but I think it's still worth knowing. It is called refluxing. So refluxing basically just lets us heat mixtures for a long time without letting all the solvent, like water, evaporating. So for example, let's just say we have a yellow solution like that one over there, and we want to heat it for a long time without having all the liquid water inside it all evaporating through this tube. So in this drawing I made, if we don't have a refluxing tube attached to the tip of the flask, what will happen is as you heat the solution, so this is like a fire, all of the water vapor will escape and you're left with basically no solution. And remember, we want to heat a mixture without letting all the solvent evaporating. So we don't want this to happen. We don't want to have barely any solution. We want to have a full amount of solution. So what we do is you use a refluxing tube. Now, a refluxing tube, as you might notice, is very similar to a condenser in a distillation apparatus or device, because water goes in and it goes out here, and it's usually cold water. So basically this, glass layer thing will condense any water vapor that tries to get out. So, maybe these water particles might want to get out through, the top. But this refluxer will make sure to minimize that effect. So what will happen is that the refluxing tube will cool down these water vapor particles and cause them to become a liquid, and this will cause them to drop back down. And if it drops back down, it's basically recycled, and then it might go back up again, but then the refluxing tube will cool it down, and then it'll condense back to the liquid and it'll move back down and then drip back down. So that's recycling the solvent like water. And that's something really cool that we could do in chemistry. So now let me ask you one question. Why did I write hot and cold? Why is the water over here cold while the water up here hot? Well, if you think about it, the water that's going in is coming from, a really cold source of water. So, it will be cold. And as the water travels up the tube, it'll leave out here warmer than it was down here, because when it was moving up this tube, it's actually cooling down the hot water vapor. And when you cool something down, you're basically absorbing the heat for it. So this gas will turn to liquid, these water vapor molecules will turn to liquid and lose heat, but in turn the water around it will absorb this heat for it and cool it down, and that's why it becomes hotter when it escapes. So that's all for now. Thanks for watching. Have a nice day.